Thank you. Danke, Friedwart. So yeah, we've been working for over 20 years together. It's a long time. Okay, good morning. Hey. I guess the textbook opening for such a talk would be to ask you, how many of you are using OAuth? But that would be probably pretty lame, because that's pretty much like asking you, how many of you are using HTTP? Right? Because, you know, OAuth is the de facto standard. It's everywhere. Everyone is using OAuth multiple times a day, to access your APIs, your whatever. There's a chance that you have used OAuth today already. Okay? So it's super popular. And I think the reason why it is so popular is because it strikes a balance between security and ease of use. Okay? It is not perfectly secure, but it is also relatively easy to implement. Yeah? And as we'll see later, that was exactly the intention of some of the OAuth spec writers. Not all of them, but some of them. We'll talk about this, why this is this way. OAuth is being used, as I said, everywhere in your mom and dad's, standard eShop implementation, up to banks and healthcare and wherever, right? And we have accepted some of the issues or problems with OAuth, and one of them, to be honest, is the absence of this thing called proof of possession, or sender constraining, as some people would call it. And if you have no idea what I'm talking about, no worries, I will explain it, okay? But in fact, yesterday I looked up my talk archive, and exactly 10 years ago I did a talk here at Troopers, shortly after OAuth was released, and I was saying, it's there now, but it's missing proof of possession. 10 years ago, okay? And have you seen this TV show? The Long Way Round? It's Ewan McGregor and his friend Charlie. They take their motorbikes from London to LA, but eastwards. Okay, so it's a pretty long way round to get to their final destination, and that's exactly how it feels like with OAuth and proof of possession. Okay, so this talk is pretty much about, I will show you some history, I will present you some failed attempts along the way, how to implement this feature, and I will show you in the end the successful attempts, how to implement this feature, which are now actually real standards and which can be used today. Okay, so my name is Dominick. For the last 20 years, I worked in the identity space. I wrote a couple of security token services, started all with, Kerberos, and then WS Security, WS Trust, WS Federation, OpenID Connect, OAuth. And it turns out the last one I wrote became a product. And that is basically what I'm doing today. I'm the CEO and founder of Duende Software, which is has a product called Identity Server, which is a framework for building OAuth and OpenID Connect token servers. Okay? And also the slides can be found here for download. Cool. So, since we all established that you're all using OAuth, probably also today already, that is the standard explanation how OAuth works, right? You have a client, you have a resource, and the client gets a so-called access token from a token server, and then puts that access token onto the authorization header with the so-called bearer scheme to call the API. Okay? That's how OAuth works, right? Now, bearer is the interesting part here. So bearer basically means it's a so-called bearer token. And what does bearer token mean? Basically, whoever has the token can use the token, right? It's like when you're losing cash on the street. If somebody finds that money, they can buy nice things. Okay? There's no binding of that money to the owner. If you lose the money, it's gone, someone else can use it, right? And that's exactly how OAuth bearer tokens work. If you lose your token for whatever reason, somebody else can use it. Okay? And that kind of assumes a perfect security world, right? That assumes that the issuer will not leak the token, the client will not leak the token, the resource will not leak the token, right? This assumes perfect transport security. This assumes that no one who has access to your reverse proxies can read the traffic in clear text, right? All of these things. So, which is kind of a risky model, right? Why do we have that model? I will explain it in a little bit more detail, but that's how it is. Okay? So now I do an audience participation question. Has anyone done WS security before OAuth? Some people? Like, you still feel the pain? In this older technology, there was a different type of token, which they called a proof of possession token, or a holder of key token, or a sender constraint token. You know, there were a couple of names of that. And the idea of that was that you can bind the token to the client application. Meaning, if the client will lose the token on the street and someone picks it up, they can't use it because there is some cryptographic binding to the owner of that token that this, other person cannot fulfill, right? A little bit like a credit card, right? So when you lose your credit card, you still have to know the PIN, potentially, to be able to use it, right? In an ideal world, at least. Anyways, so that's the model we have since 2012, and nothing has changed, really, right? And then in the last couple of years, there were a whole bunch of independent initiatives that decided that this is not secure enough. Right? This might be fine for doing doing your restaurant rating on TripAdvisor, but this might not be fine to do a bank transaction. This might not be fine to do something healthcare related. So I worked very closely for the last 5 years with the Norwegian healthcare system, where they redone everything using OAuth and OpenID Connect, and they said like, bearer tokens. That's a bit risky, right? If somebody leaks that token. So in Norway, for example, they have an API where you can basically notify the government that someone has died. He's dead, okay? That's used by hospitals, for example, and they ping the ping of death, if you like. Yeah. You don't want that to be secured with bearer tokens, right? If something goes wrong there, you can imagine you're in big trouble if somebody plays a prank on you and says, hey, you are dead, to the government. Yeah, there's a whole workflow kicking off. So anyways, healthcare, financial industry, right? Financial APIs, the Payment Service Directive number 2 was a big thing. In the US, they have this enterprise mission tailored OAuth profile. They all came to the conclusion that bearer tokens is not secure enough for certain situations. Okay? So what to do now? Well, as I said, if you remember WS security, right, 2004, long time ago, that was like a serious lineup of enterprise people here that specified that stuff, right? That was the technology before OAuth, right? And they did have bearer tokens, but that wasn't their default choice. That wasn't their recommendation. What they had was proof of possession tokens. So, let's recap very quickly, how did proof of possession technically work 20 years ago, okay? So, basically, it's always the same. Here's the client application, here's the token service, and here's the resource that you want to call. Yeah? So the way this worked is basically the client generated a secret. Yeah? Might be a symmetric key, might be an asymmetric key, whatever. And then the client made a token request to the token service, encrypted that token request with the public key of the token service, and sent that secret along encrypted. Okay? And then what the token service did is it created a SAML assertion, right? SAML was the thing by the time, that included the secret and encrypted the SAML assertion with the public key of the resource, right? And then the client took this SAML assertion, sent it along, and signed the XML body with the secret. Yeah? So in other words, that secret was never in plain text on the wire. Yeah? And also, 2004, we didn't have TLS by the time, widely deployed, especially in enterprises, right? So then what the resource had to do was decrypt the secret, decrypt the SAML assertion, get the secret, and validate the signature of the XML body with the secret. Okay? That is technically working. What's the big issue here? Key management, right? The client needs to know the public key of the STS upfront. The STS needs to know the public key of the service upfront, right? And what did people not do ever? Key rotation, right? Because if you're starting to rotate those keys, all of these static config files, typically, they go out of sync. It didn't work. Okay, so that was the solution that we had. It wasn't the thing that people wanted to move forward with. Okay? So after that came OAuth 1.0. Nobody ever talks about OAuth 1.0 anymore. And because it wasn't a very successful protocol. Why? Because it was very, very complicated. Okay? The only reason why OAuth 1.0 became a thing was because people even more hated WS star. Right? Nobody liked XML and SAML and all of these things, so Google sponsored this effort to build a simpler protocol based on, web standards, HTTP, JSON, and so on. Right? So they hired a guy, very important, called Aaron Hammer. Okay? So Aaron Hammer was a security guy. They hired him. They explained to him the problem they want to solve, which was pretty simple. How can you authorize a third-party application to access your Google Calendar without you having to disclose your Google password to the third-party application? Right? That was the whole, mission statement. And guess what? What Aaron came up with is what he called signature-bound tokens. Okay, so right from the start, OAuth 1.0 had proof of possession as the only way to do it, really. Because Aaron said, anything else would be too insecure. Okay? So let's have a look at the spec. So if you look up the OAuth 1.0 spec, you have 3.4 signatures. You are now basically going over at least 10 pages of instructions how to canonicalize strings, how to canonicalize query strings, how to canonicalize headers, and how to line them up, and how to sign them, and how to sign URIs and request parameters, and so on and so forth. And you ended up with a lot of confusion. And what do you think? How many average developers were able to implement this? One. Aaron was a developer, so he could do that. Yeah. And when you asked Aaron after that, looking back, he said, I don't like this at all. Yeah, the premise was they were hosting their hosting provider back then didn't support TLS, so they had to find something that has kind of TLS-ish properties, and it had to be implemented in PHP. Okay, so that basically was what they came up with, and he didn't like it at all. Okay, so it was pretty apparent, this is going on and on. Yeah, yeah, and then you do RSA, right? 20 years ago from JavaScript or something. Yeah. So this didn't really work out. Okay. So pretty quickly after OAuth 1.0, they started working on OAuth 2.0. Okay. And of course, they hired Aaron again. Aaron was the IETF spec author of 1.0, so why wouldn't he drive the effort for 2.0? But guess what happened? Suddenly, everybody wanted to have a simpler solution to the API access control problem, right? Microsoft and Google and you name them. Basically, all of the big enterprises, they were just done with WS security and wanted something else, that they sent all of their people to the IETF meetings, right? And what did they ask for? A simpler version of OAuth 1.0. And what was the first thing they wanted to drop? Message-bound tokens, signature-bound tokens. Okay, because it was too complicated. So, Aaron posted in 2010, bearer tokens are a terrible idea. Okay, and he said I'm trying to stop this movement here. That was 2010. 2 years later, he said, I'm withdrawing my name from the specification. Yeah, because all of the Microsofts of the world, you know, they just had more people in the IETF meetings. And you know, if you've ever been to an IETF meeting, it's like voting and so on, right? And if you are outvoted, yeah, so the way he said it, like, it felt like they all came with their RV campers and parked in front of the IETF meeting just to be able to vote for simplification. Anyways, so he says, yeah, it's less secure now, right? And unfortunately, all of that stuff is gone. You have to go to archive.org to read the original. Anyways, Aaron was very, very, very unhappy. Okay, so he left the committee and spent his time creating artwork. For example, this one. Or this one, if you remember the original OAuth logo with the cute little kitty, that's roadkill now, okay? And he did a last talk where he coined a new hashtag for Twitter, where he explained in very much detail why OAuth 2.0 is basically the worst protocol ever, okay? Yeah, so as the last thing he did before leaving the IETF, he demanded that proof possession tokens will be developed or released after they did the bearer one. So basically, the reason why there are two specs now, RFC 6749, which is for getting the token, and RFC 6750 is for using the token, is that there was a plan for RFC 6751, basically, which was called proof of possession token usage. Okay? Never happened. The only thing that happened was 1 year later is they wrote this one here, which is a threat model which very explicitly points out the security properties of bearer tokens. Okay? So that was kind of like, you know, history. Now, there were actually a couple of attempts to reintroduce proof of possession afterwards. Aaron wrote another spec, which he also abandoned, which was about HTTP message signing. So they tried to adopt this and turn this into another spec. People lost interest in it because it was as complicated as OAuth 1. And why? Well, because it's a really hard problem to solve. Okay, there can't be a super simple solution to this. Yeah, so people lost interest. It expired, right? Very IETF-ish. The only thing they could agree on was if there would be proof of possession as a technology, that's how we would represent it in a JSON Web Token. And that was the only spec they ever turned into an RFC in absence of all of the other technology that was needed for that. Everyone was hoping that there would be a simpler solution, and they all hoped for the transport might help us out. Okay, so there was this thing called token binding. Does anyone remember token binding? HTTP token binding was a TLS extension, basically, which allowed the application layer to get a key from the TLS channel and use that key to bind cookies and access tokens to the TLS channel, which solved a whole bunch of problems. For example, cookie exfiltration, token exfiltration in the browser. You couldn't use that token on a different TLS channel anymore. Right? That would have been perfect. But that only works, of course, if the browsers would implement that technology, right? And then this happened. Google decided to remove the technology from Chrome. Yeah, just out of the blue, this thing happened. Never was any justification given why they're doing it. They just removed it. There are lots of theories around this, why they did it. Some more on the conspiracy side of the house, and some of them on the more technical side of the house. But ultimately, Google wasn't interested in that. They removed it, and this thing was dead in the water. Okay? So yeah, still no proof of possession, and that is from 2018. Cool. So now this thing comes along, FAPI. FAPI stands for Financial APIs. So if you remember, PSD2, the Payment Service Directive 2, was this European initiative to turn banks, to force banks to open their banking APIs, right? There was a famous deadline, I think it was 2019, that everyone missed. And guess what? And to become PSD2 compliant, you had to implement FAPI. And guess what FAPI said? Your tokens must be proof of possession tokens. But there was no technology for that. Okay? And that's why every single bank couldn't make the deadline because the technology wasn't there. But suddenly there was a big interest from the industry, especially from the money industry, right? Banks, they have money, they can sponsor maybe technology, right? So the IETF was kind of forced to produce a stopgap solution to enable banks as soon as possible to do FAPI. And for FAPI, they need proof of possession. Okay? And this spec was released. The OAuth mutual TLS and certificate-bound access token spec. Okay? So the idea was they looked at the banking industry and thought, okay, hey, this is an industry that has PKI, typically. This is an industry that knows how to use MTLS, and we can achieve proof of possession by using MTLS and client certificates and can then bind access tokens to an X509 certificate. Okay? So that was produced. As I said, it was a stopgap solution. No one really was interested in writing that spec, but there was a big need, so to speak, in producing something. Okay? So I'm sure some people or most of you know how mutual TLS works. It is pretty complicated. For those who don't or can't remember, I found this very good explainer video on YouTube. That's pretty much how it works. Okay? Good. Ultimately, what mutual TLS does is it does server authentication, it does client authentication, and what we mostly care about is there's a cryptographic element, a key that gets negotiated along the way that we can use. Okay? So let's see how mutual TLS works with proof of possession. Pretty similar idea, but this time we are generating or using an X509 certificate with a private key. Then we are opening a mutual TLS, an MTLS channel to the token server, request the token, use our X509 certificate, and then what the token server will do is issue us the access token and embed the hash of the X509 certificate inside the access token. And now, what the client will do is use the same X509 certificate with MTLS to open a channel to the API and use the same X509 certificate with the access token, and then at the receiving end, what the service will do is it will validate the access token, get the hash of the cert, compare that with the hash of the cert from the TLS channel, and if they match, the client has proven that he owns the token, proof of possession. Okay? If you would lose that token now for whatever reason, the attacker or whoever will try to use it would need to have the private key. And since they don't have it, they can't do it. Okay? That's how MTLS works, or MTLS POP. Yeah, and that's how that looks like. Yeah, so that's a JSON Web Token, shortened, and that is that new claim that they standardized in the IETF called CNF, confirmation. Yeah, and that means the X509 thumbprint in SHA-256 format, and then that is, I think, base64 URL encoded or something like that. Okay, so that basically is how that works. So I have an MTLS-enabled token server on my machine. And you see, if the token service supports MTLS, it has a special element in the metadata, which is called MTLS endpoint aliases. And that basically says, if you want to use MTLS, don't use the normal token endpoint. The normal token endpoint would be this guy. Okay? Don't use this one, use this one. And that is on a different subdomain, which requires mutual TLS. Okay? And then, yeah, well, I could run a demo now. It would be very, very unexciting because there would be a token, right? And the token would contain a thumbprint. But you get the idea, right? that special subdomain requires MTLS, and there's a whole bunch of network infrastructure necessary to make this work, as you can imagine, right? That the real application runs on this domain, the MTLS one on the subdomain. There are some, some Nginx or whatever reverse proxy magic going on with certificate forwarding, and so on. And that is exactly why this technology is not really popular, right? So if you have an existing MTLS and PKI infrastructure, then this is basically pretty easy to implement. Yeah? They don't even require chain trust. You could use an ephemeral certificate that you generate on the fly, as long as you're using the same cert for the token request and that you're using for the API access, right? But still, right? I mean, you need to have some infrastructure in place for that. So for banks, that was kind of easy to implement, while working on the IETF and in the mailing list, especially the cloud providers said, no, this is not going to work for us, like AWS, Azure, and so on. Let's imagine you're having a mobile application running on some phone, on some random network. Being able to guarantee that from this random network, you're going to get an MTLS channel all the way through to the backend server is not likely to happen. Yeah? So, yeah. Anyways, it fulfilled the FAPI requirements. Let's put it this way. Okay? But at the same time, people started working on an easier version, quote unquote easy, because, as I said, there can't be an easy solution to this because it's a hard problem to solve. But basically the idea was, can we do the same without the network infrastructure, without MTLS, without PKI, without all of that reverse proxy madness that we need for that, and so on. And then they kind of came back to application level message signatures, but this time a little bit easier to use. And that is this new spec, actually. It's actually not even an RFC. It is in the hands of the RFC editor, whatever that means. But what it means is it's going to be an RFC soon. Okay, so no one, it passed what they call the last call, so no one can change it anymore. So it will be an RFC in the next coming weeks, I guess. We implemented this just recently, even if I always said, like, I will never ever implement an RFC before it's published, because that can go really bad. But this time we did, because I think it's important. And that is kind of like in my mind, will be the standard way of doing proof of possession in the future. Okay, because it can be completely done at the application layer, in application libraries, and so on. No MTLS necessary for that. So, how does that work? That's the last one. Basically, the way DPoP works is that you're doing all of your normal HTTP business, right? Nothing changes here, but you're always adding a special header to every single network call, which is called the DPoP header. And what this header contains is the so-called proof token. And what is a proof token? Basically, a proof token is a JSON Web Token that has a public key in the header and some algorithm and so on. And then basically it has some data like the HTML, so the HTTP method used for the request, the HTTP URL used, when it was issued, the issued ad claim, and JTI stands for JSON Web Token ID, so a unique ID which you can use for replay protection. Yeah? And then basically, and the signature that proves the knowledge of the private key that corresponds to the public key. Okay? So in other words, the client generates a public-private key pair on the fly, makes an HTTP call, sends along that proof token. So now the recipient, in that case the token server, can verify that the client actually knows the private key that belongs to this by looking at the URL, by looking at the method, and the public key. Okay? Cool. So what we're getting back now is an access token again in OAuth with a confirmation claim. But this time, the confirmation claim does not contain the hash of the X509 certificate. It contains the base 64 URL encoding of the JWK SHA-256 thumbprint of the public key, which is my favorite sentence in the whole slide deck. Okay, So with that, basically, we are binding the access token to the private key of the proof token. Okay? Cool. So now, when the client now does the resource access, it sends along the access token we've just seen. It's not bearer anymore. As you can see, bearer is gone. It's now DPoP. Okay? And along with the DPoP authorization scheme, it sends along a new proof token for every single HTTP request. Okay, so for every single HTTP request, the client needs to create a new proof token using the same public-private key pair that was used to request the token in the first place. Okay? How does that proof token look like? Very similar. Same public key, a unique identifier, HTTP method, HTTP URL. Now this is interesting. That is the hash of the access token. Okay? So with that, the proof token gets bound to the access token. Right? And with our confirmation claim, the access token gets bound to the proof token. So there's a two-way binding now between the key material in the proof token and the access token. Okay? And then again, the signature that proves that we know the private key. So, to summarize that, right? We generate a key pair, create a proof token, send the proof token to the token server, get back a token response with an access token containing the hash of the public key that is used to sign the proof token. And then we are sending the access token and the proof token to the service. And then the service ultimately needs to validate both tokens, make sure they are both valid, and then check the linking both in one direction and the other to make sure they have not been separated somehow. Okay? That sounds like a really simple solution to the problem, right? But is it perfect? That's how the spec looked like up till revision 6 or 7 or 8 or something. Okay, and people said, "Oh, finally, we've done it. We solved the problem. It's all super easy." And then it turns out Microsoft went and implemented it internally, and one of the guys at Microsoft found a couple of problems with the protocol. So let's see. Sometimes simple is too simple. The first complaint was that all we are really signing here is only the HTTP method and the HTTP URL, right? We're not even signing the query strings, just the URL. Okay? So there was some discussion like, is this good enough? And to be honest, it is good enough to prove that you know the private key, right? But there's still some wiggle room here. Yeah? Why didn't they go for query string parameters? Well, because now suddenly we would be again in the whole business of how do you canonicalize query strings, right? Because like you might send A equals this, B equals that, C equals this on the sender. Now a reverse proxy comes around, shuffles around the query strings and sends them long, and the signature wouldn't match anymore, right? So that was business they didn't want to get into. Same goes for headers. Same goes for the body. Right? So they said, okay, you can do all of these things. Yeah? You can do more, you can sign as much as you want, but the spec does not mandate it. It's up to you to increase the complexity. The other thing is, you see these proof tokens, they have this issued at claim. Okay? So basically that tells the recipient when was the token created. Now it's up to the recipient to build their own little policy if they want to accept that token. So with the absence of an absolute signature, right, basically what we're saying is we're going to accept that token if it's not older, let's say, than 1 minute. And for 1 minute, we're going to stick it into our replay cache using this JTI, this unique value here. And if we're going to see that token twice, we're going to reject it. Okay? That's how that works. That means every single proof token recipient, the token server, every single API in your system needs to implement replay detection now. Okay? At cloud scale, potentially, which is not easy to implement, as we know. Okay, so there's complexity here. But the fun thing was what the guy from Microsoft found is, yeah. So basically he had some engineer working on the implementation of that, and he found out basically if he has access to the key material, right, of the proof token, he can, for example, generate a proof token for tomorrow 3 o'clock. Right? All he has to do is create a token with the issued ad, set to tomorrow 3 o'clock, sign this thing, because he knows maybe tomorrow at 3 o'clock I have a window of possibility to do a replay attack on the access token and send along the proof token. So basically they found the problem that somebody could create tokens for the future. Okay? And for example, if you're having a cross-site scripting attack in your application and it remote controls your JavaScript to create tokens for the future, okay? That's why we can't have nice things in security, because it's complicated. Yeah? They thought, okay, the issued ad is not good enough. And the next thing is, the issued ad is the clock of the client, right? So if on a mobile phone I create a token, the issued ad will point to my current time. What if I have this game on my phone which expires tomorrow and I moved my date and time to 1 year before? Right? My issued ad will be 1 year old. It will not work anymore, right? What if my clock is just off, right? Remember Kerberos, 5 minutes? Yeah. So these are all real-world problems, yeah? So the only way to solve this is to add more complexity. And that is called server-issued nonces. Okay? So if somebody sends a proof token to the recipient, and for whatever reason the recipient is not happy with that token, maybe the clock is off, maybe, you know, the issued ad would be rejected, maybe they need the extra security, then what the recipient can do is return a 400 error, use DPoP nonce, and send a random value back to the client, and then the client has to repeat the HTTP call and put that nonce into the proof token. That sounds like not a big deal, but if you implement the protocol, that is a big deal. Because suddenly now you have state management on the server, you have state management on the client, you are supposed to reuse that nonce until you get announced a new nonce. Okay? So anyways, it's of course all doable, but there are some repercussions here. And which goes back to my point, there is no simple solution to the problem, I think. Yeah, it is just a hard problem to solve. Now, to summarize that, yeah, what's good about DPoP? It doesn't need any special infrastructure. It can be implemented with widely available tooling today, right? Every platform has JWT tooling. Every platform has crypto like RSA, SHA, EC, and so on. The cons is, well, A, it's new. It's not even RFC yet. And it requires code changes everywhere, right? In the token server, in the client, in the APIs. We need to implement the validation, the replay caches, and potentially the nonce handling. And I can totally see that initial implementations will just skip the nonce part because it's easier to implement that. But the spec says you must be prepared for server-side nonces. Okay? So, I guess, does now everybody in this room have to go away and implement proof of possession tomorrow? I don't think so, right? Aaron Hammer, even if I respect Aaron very much, I think he was wrong. The sky did not fall 10 years ago because we only had bearer tokens, right? Yes, on paper, they are less secure than proof of possession tokens. But there are some mitigation techniques, right? You have transport security, you have lifetimes, and so on. So not every single API, not every single website, in my opinion, needs proof of possession. But if you are building a banking system, or a healthcare system, and you implement the ping of death, or if you are, for example, implementing the browser-based portal for your cloud infrastructure, and you store your access tokens in local storage, like some do, I would think twice about this. They are pretty powerful tokens, right? And you don't want that anybody who leaks them, you know, for whatever reason, that they can be reused by an attacker. Okay, so I guess the summary of all of this is, if you need that security properties of PoP, there are ways now to implement this, but it does not come for free. If there are any questions, now's the time, and thank you for your patience.
Thank you, Dominic. Are there any questions? I'm waiting for you posing a question.
So I don't know if you know about the Microsoft implementation, because they have already been adding this to their platform. Do you know if it's based on like this DPoP, or you have no idea what they're actually using?
So Microsoft, being Microsoft, they invented their own first, which is out there. I think some application libraries do use it. And it's more like the old school HTTP message signing that we used to have in OAuth 1. But at the same time, they implemented the DPoP spec while it was being developed. And my guess would be that they are switching, or they're going to have both implementations for a very long time going forward. And the Azure portal will have more options. But yeah, ultimately, they want to switch to this. And Microsoft implementing this, they found the signature in the future problem, for example. So they're working on it, but of course they had something on their own first.
All right, thanks.
Further questions?
Yes. So maybe I don't understand the OAuth complexity good enough, but so if it's a stupid question,
I will answer it anyways.
Yeah, so for OAuth, right, there are different flows that you can do. How does the POP, how does that work with the different OAuth flows?
It's flow agnostic. Because
it's flow agnostic.
Every flow, the ultimate goal of every flow in OAuth is to return an access token to the client application. And that's where DPoP comes in.
Okay, thanks.
The quick protocol, will it have an impact?
No.
Or change with?
No. Quick is HB free, right?
Yeah.
No. It's just, you know. I mean to be honest, that's not your question, but yeah. I should mention it. The HTTP working group at IETF are working on it on the official HTTP signing specification. And that will sign everything. URLs, headers, bodies, everything. And it's super complicated. And there was a call at the IETF OAuth working group if they want to adopt access token binding for HTTP signing, and the answer was no.
Thank you.
Hi, yeah, my name is Linus. Thank you for the talk. Do you know if like a DPoP token or POP token will be mandatory in some new OAuth standard, like 2.0, 2.1?
No,
or like in the future?
So the goal of 2.1 is to not change OAuth. So maybe you are aware of semantic versioning in software development, where you say like a small version increase should only add features and not break the existing ones. It's the other way around in the IETF. They're removing stuff, but they're not changing existing stuff. For example, in 2.1, they're going to remove resource owner password grant. They're going to remove the implicit flow. You know, that stuff will go away. But DPoP is mandatory for FAPI2. So FAPI2 is the revision 2 of the financial APIs. And when you remember, I think, was it my third slide or something? This one here. So FAPI used to stand for financial APIs. And now they realize we have the same security requirements in healthcare, in enterprise scenarios. So they renamed it, because they still had a domain, so they had to rename it without changing the characters. So it's now called financial grade APIs. And it's for all APIs which need comparable security to finance. Okay, and indeed in FAPI2, DPoP or MTLS is a requirement. You have to choose one of the other, but not in the plain OAuth spec.
Okay, thank you.
Are there more questions? No? So thank you very much, Dominick, for your highly
welcome.
specialized talk. Thank you.